Hi everyone. Good afternoon. Good afternoon, class. Just checking. Can you hear me and see my screen? Good afternoon, class. Okay. All right. All right. Thanks. All right. Okay. Let me take your attendance first. Before we start the class. Okay. I'll just call your attendance. Brenda. Brenda, are you here? Okay. Tan Su Bian. Tan Su Bian. Tia Chai Siu. Chu Zhang Hing. Chu Zhang Hing. Are you here? Chua Yu Yang. Chua Yu Yang. Ernest. Ernest. Okay. Go Kian Sing. Go Kian Sing. Hu Hing Dong. All right. Ku Bun Kyung. Ku Bun Kyung. Are you here? Okay. Lao Lok Jing is here. Li Zilim. All right. Lim Chun Wei. Lim Chun Wei. Lim Wen Yang. Lim Wen Yang. Lim Yong Chuan. Lim Yong Chuan. Long Yao Ting. Good afternoon. Lo Tiong Lia. All right. Lu Jimin is here. Ng Han Xiang. Ng Han Xiang. Ng Wei Hong. Okay. Ng Wei Hong. All right. Ong Mei Lin. Hong Shui Wen. Kwa Yi Han. Kwa Yi Han, are you here? So Yan Cheng. All right. Tan Xin Shen. Tan Xin Shen. Teo Leong Ho. Okay. Tan Xin Shen. Teo Leong Ho. Teo Yi Si. Wong Chung Yi. Wong Ka Shing. All right. Yong Wing Liang. And Yong Xie. Yong Xie. Xie, are you here? Okay, good. Kwa Yi Han. Kwa Yi Han, are you here? Chu Zhang Hing. Okay. Go Kian Sing. Go Kian Sing. Go Kian Sing, are you here? Lim Chun Wei. Lim Chun Wei. Lim Wen Yang. Lim Wen Yang. Okay. Lim Yong Chuan. Kwa Yi Han. Kwa Yi Han. Okay. I'll check your attendance again in a short while. Now, oh, today we are going to today we are going to review the materials on RTS. RTS. Okay, so these RTS the materials are important because they will help you to complete your assignment. Okay, where is it? RTS, real-time systems. Real-time systems. There you are. Okay, so as you know, your assignment one, where you press the buttons to make the LED flash, right? So that's a real-time system. Okay, because you're doing a few things in parallel. You are controlling, you are making a light change color, right? Color sequence is changing colors. And then at the same time, you're waiting for somebody to press a button to change the light to flashing white. And at the same time, you're also waiting for somebody to press a button to change the speed of the flashing. Okay, so you're doing a few things at the same time. So how do you deal with this concurrency? Concurrency means we do a few things at the same time. How do you deal with this? So we explore the topic of developing a program to run in real time and also taking care of concurrency issues when we look at these materials on real-time systems. Okay, so take note of this because you will use the techniques presented here to complete your assignment. Okay, so let's look at the materials. Now here, so you notice that this looks familiar, right? This looks familiar, okay? Because you see, so I have a board here. This is the MKL25Z board. So this is the third guy that you are introduced to in this subject. First one is LPC1768, right? Then the second one is STM32F, and then now I show you another one, MKL25Z. Don't worry, that's all there is. I'm only going to give you 3 examples of our controllers, just so you can see, you can compare between them, right? 3 very popular microcontrollers. Okay, so we have this mouse controller here. It's connected to 2 switches, switch 1 and switch 2. And if you look at the way it's connected, we call this active low switch. Active low switch, because of when you press the button, you activate the button, it will connect to logic 0, low logic. So when you activate the button, the input is low, right? If you don't activate the button, the input will read high because of these 2 pull up resistors. Okay, so we call this active low button. The LEDs are also active low because you activate or you turn on the LED with a logic 0, low logic. Okay, so these are active low LEDs. Now, we want to write a program to do this. You press switch 1. When you press switch 1, the RGB LED will flash white. They will be flashing white. When you release switch 1, then it will do a color sequence. Red, green, blue, red, green, blue, red, green, blue. Of course, your assignment, you got slightly more colors. You got 8 colors to cycle through. Okay. And then, okay, so now, let's say we didn't press any button. So it's going red, green, blue, red, green, blue, red, green, blue, right? When you press switch 2, it will change faster. So red, green, blue, red, green, blue, red, green, it will change faster. When you release switch 2, it goes back to changing slower. Red, green, blue, red, green, blue. You press switch 2, it goes red, green, blue, red, green, blue, red, green, blue faster lah. Okay. And then if you press switch 1, the red, green, blue will change to flashing white. So if you press switch 1, it's flashing white. And then you press switch 2 without releasing switch 1, it will flash white faster. Okay. Let's say now you press switch 1, your finger is still there. You press switch 1, finger still there. So it's flashing white. Then with your finger pressed on switch 1, you use another finger, you press switch 2, then the flashing white will flash faster. Okay. So here is how the board looks like. This is how the board looks like. Okay. So there is this one is the RGB LED. You don't need this hardware. I'm just showing it to you only. This is the RGB LED. Okay, the red, green, blue LED. So this example program, you see the different colors. Okay, that's white. So do it again. This is red, this is green, this is blue, and this is the last color is white. Okay, so if you turn on all 3 LEDs at the same time, red, green, blue at the same time, you get white. All right, let me show it to you again. So you get red, green, blue, and white. Right? So I want to see the white again. Doesn't look very white now. Red, green, blue, and how's it? Oh, does it look white? It looks white now. It's white now. So this is white. Okay. All right. Let me minimize this. So we're going to write this program, and we're going to do it in real time. So how do we do it? How do we approach this? Well, the simplest way to program this is super loop. Super loop. Right? What's a super loop? Super loop means you put all your code, super loop, you put all your code inside forever loop while one. You write your program, you put all your code inside a while one. So this is the while one loop. This is the while one loop. Okay. So first you initialize the delays, then you initialize the GPIO, and then you check if switch one is pressed. So if switch one is not pressed, that means no flashing white, then you will turn on red, delay, turn on green, delay, turn on blue, delay, then you check got press switch 2 or not. If nobody press switch 2, so maintain with the long delay. Long delay is default. Long delay is default. Then you look back, and then is switch 1 press? No, then you do red, green, blue. Is switch 2 press? No, then you look back. Like this. Okay, now, if switch 1 is pressed, you do red, green, blue. After that, you check switch 2. If switch 2 is pressed, then you will change the delay to short delay. Change to short delay. So when you come back here, the red, green, blue will have a short delay. They will change faster. Okay. Now, if switch 1 is pressed, then instead of showing red, green, blue, you will show turn on all 3 at the same time, you get white color, right? And then turn off the white color, right? So you on the white color and off the white color, long delay, default. Otherwise, it's short delay. So how is this program written? Okay, let's look at the program now. Let's look at the program now. So this is the program, right? This is the program. Let me zoom in a little bit. Let me zoom in a little bit. Okay, so this is the start of your program. This is the start of your program. So you include this header file, mkl25z4. So this header file, I already added it here already. If you go to your Google Classroom, you look at your lecture discussion, lecture notes, you see the header file is here, right? This is the header file, mkl25z.h. Just for reference. just for your reference. Okay, so this is your header file. Okay, it's your header file. So if you see anything in this program that doesn't make sense, it will have been defined inside the header file. Okay? Anything that you see here that you don't know what it is, just go and look it up inside the header file. Okay, so now let's look at these hash defines. These hash definer, they are called preprocessor directives, right? Who is the processor? It's not your microcontroller processor. You know, when you see somebody say something like this, preprocessor, this preprocessor is actually referring to your compiler, right? It's your compiler processing. Okay, compiler processing. You know, when you press the build button, when you oops when you press the build button on your development tools, what happens when you press the build button on your development tools, right? You will actually launch the compiler program, right? You launch the compiler program, right? So when the compiler program runs uh, we say the compiler is processing the C code, to generate assembly code, to generate uh, corresponding corresponding assembly code. Okay, so you press the build button on your development tools, you are actually launching a compiler program. The compiler, what it does is it processes your C code, right? How does it process your C code? It will translate your C code to corresponding assembly code. That's what the compiler does. Okay. So when we say preprocessor, it means before before compiler processing. Okay. Before the compiler starts doing its job. That's what we mean by preprocessor. Post processor means the things that you do after the compiler has completed its job. So preprocessor or pre-processing is the things that happen before your compiler starts running. Okay, so before your compiler starts running, we want to tell your compiler something. Those are called preprocessor directives. So when you see preprocessor directives, these are actually commands to the compiler before it starts its work, right? It's actually commands to the compiler before the compiler starts doing its job. So what are you telling the compiler? You're telling the compiler here, right, that whenever you see red LED position, please replace it with number 18. Okay, why that? Why that? Because as you can see from here, we are connecting the red LED to port B pin 18, the green LED to port B pin 19, the blue LED to port D pin 1. Okay, switch 1 to port B pin 8 and switch 2 to port B pin 9. So why we do these connections? That's because we are using this board. Right? And the connections is already hardwired. Okay, so that's why we use those pins because the connection is already hardwired to these ports. Okay. Now, when you write your program to make the program easier to read, we don't use 18. Okay, you don't use 18. Instead, you say red LED position. Okay, so inside your program, instead of using the number 18, we just replace it with this red LED position. So we call this a symbol. We call this a symbol. It's a name, but the terminology, instead of saying name, we say symbol. So this is a symbol. Okay, so we tell the compiler that please replace this symbol with 18, please replace this symbol with 19, please replace this symbol with 1. Okay, replace this symbol with 8, replace this symbol with 9. Because inside your program, if you use 18, 19, 1, 8, and 9, it's difficult to read. But inside your program, if you say red LED position, things like, for example, here, you read the program, it says uh, mask red LED position. So oh, this is, we are referring to the IO pin where the red LED is connected to. If you write here 18, then we will scratching your head. Mask 18, what's that? But if you say mask red LED position, then we know, oh, okay, this is the pin number that the red LED is connected to. So the hash defines just makes our program easier to read. Okay. All right. Then you notice there is this line. So this line is called a macro. This line is called a macro. This line is called a macro. Okay. So you're telling the processor, the compiler, whenever you see this, please replace it with this. Okay. So for example, if you write mask 3, right? This is this is actually you take 1 left shift by 3. Okay, take 1 left shift by 3. This is what it means. Mask 3 is actually 1 left shift by 3. You see, mask X. So for example, if you write port B PDOR, let's say I write something like this equals to mask 18. I write like this. Okay, what this actually means is it actually means it's the same as this equals to 1 left shift by 18. Okay, so what's one left shift by 18? Why we want to write 1 UL? Because you see if you don't write the UL here, the 1 can be 0 binary can be 0, 0, 0, 0, 0, 0, 0, 0, 1, or it can be 0, 0, 0, 0, 0, 1. Okay, it can be either case. Actually, it depends on your microcontroller. It depends on the compiler also. So if you just write one, no, if you just write one like this, the one can be like this. It can be like this. So to play safe because I'm dealing with 32-bit numbers. I want this. I want this number. Okay, I want a 32-bit one. So how to make sure that I get a 32-bit one? So I write like this, 1 UL. UL stands for unsigned long. That means you're telling the compiler specifically, please give me a 1 that looks like this. It's a 32-bit one. So you put the unsigned long there. Okay. And then you left shift by 18. So left shift by 18 means the one you left shift by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You put the 1 here. Okay, put the 1 there. So the 1 goes there. Becomes like this. Okay, the 1 gets left shifted by 18. Right, the 1 is like this. This is the 1. Gets left shifted by 18, so you get this. Okay, so what is this actually? You see that everything is a 0. Everything is a 0 except this bit becomes a 1, right? This bit becomes a 1. Right? So this is like a mask. This is like a mask. You know what's a mask? A mask is okay, you see let's say I got a picture here. Let's say I got a picture here. So I got some stuff here. I got some stuff here like this. Okay. But right now you just want this particular part. You just want this particular part. So what do? You go and take a black piece of paper. You go and take a black piece of paper. Okay. And then you go and cut cut a hole right there. Cut a hole right there. Right? Cut a hole right there like this. And then you just remove all the other stuff. Oh, this would be easier. Then you just remove all the other stuff. Okay, you just remove all the other stuff. put black color here like this. So this is called mask. No superhero mask. Yeah. Right, this is a mask. So you cover everything except the part that you want to see. Okay, this is what we mean when you see the terminology mask. Okay, so you see here, where is the mask? All the zeros here, this is the mask. This is the part that you want. This is the part that you want. Okay, so now if I want to mask everything except bit 18, so what do I do? Okay, what do I do? So I take port B PDOR, this is the output data register, is equals to this one, or with that. Okay, so I do like this. That means I want to set bit 18. This means set bit 18, right? Set bit 18. So what's the easier way to write this? An easier way to write this is I just put PDOR. Short. This is the shorthand. You write like this. This is the shorthand. Okay, they're the same thing. So this means port B PDOR is equals to port B PDOR or with this value. Okay, shorthand. Now, instead of writing like this, and even easier to understand, even easier to even easier to way to understand this would be I just write port B PDOR is equals to port B PDOR or with mask everything except 18. Okay, so we use the macro, right? So instead of writing so long like this or so long like this, I just, because this is a piece of code that is very often, very frequently used. It's a piece of code that is very frequently used. So I just create a macro for it, macro, right? So the macro is this one. It's like a function, but function, you will jump to the code, the function code, but you don't jump to the function code. Whenever the compiler sees mask x, it's going to replace mask x with this expression. Okay, so you can have a slightly longer expression also, but it's something that is very frequently used. So I want to cover everything except bit 18. Okay, that's how it's used. Right, coming back here. So then we define some constants. We got the white flashing delay for slow is 400. White flashing delay for fast is 200. The RGB color sequence delay, slow is 4,000, fast is 1,000. So what's this 400, 200, 4,000, 1,000 for? They are used in our delay loop. Here is the delay loop. Okay, you see it. Okay, here you have this delay function, right? So this delay function, you give it some integer value, right? So you give it some integer value. So what's it about? So let's go down and look at it here. So this is your delay function. This is your delay function. Okay. So you give it some value. Okay. So how does it work? This is your delay function. Okay. This is your delay function. So you give it some value. You give it some value. So let's say you give it 4,000. What happens? What happens if you give it 4,000? Then it will take uh, it will take 4,000 minus minus, right? So this will look like, let me just do some indentation first, so the program is easier to read. Okay, so you can see here, the delay function, if you give it 4,000, you give it 4,000, right? Then it's going to loop 4,000 times. So while 4,000, so as long as this value is not zero, you stay in this loop. So you will only exit this loop when you go to zero. So okay, initially it's 4,000. Then inside you set n to 1,000, and then while n 1,000, so you go back, minus minus become 999. You go back, minus minus again becomes 998, 997, 996. So you're going to loop here 1,000 times. Once you're done, you're going to come out. decrement this to 3,999. And then you go inside again, loop another 1,000. So effectively, you're going to loop here, how many? 4,000 times 1,000. That's very long, some delay. So that's how you create your delays. We call this a software delay, because the delay is created by the processor. Processor is stuck here, looping until the delay is up. So this is your delay function. Okay. So is this type of delays, we only use it for the simplest programs because it's very bad way to do things. The processor is busy looping here for this delay, and the processor cannot do other things. Okay. Because delay is something that is so common now. Therefore, microcontroller manufacturers, they give you some hardware just to do create delays. We call that a timer. Okay, microcontrollers have a timer circuit built in that will help you to count delays. So you don't have to get the processor stuck there looping to create the delay. You can just program the timer. You tell the timer, okay, give me an interrupt signal after 1 second. You know? It's just like your alarm clock. So then you don't have to keep track of the time. You don't have to keep counting here. You just do other things. When the 1 second is up, the timer will interrupt you. Okay, that's the idea. All right, so coming back. So we got our delay already. Now, how do we turn on the LEDs? How do we turn on the LEDs? So we got two functions here. We got Gpio init, which is to initialize the I/O pins. We come back to that shortly. Now let's look at control RGB LEDs first. Control RGB LEDs. So this is the function to turn on the LEDs. So I got three inputs: red, green, and blue. Okay, if you call this function control RGB LEDs, I got three inputs: red, green, and blue. So you see here, this is how you use it. This is how you use it. Okay. So here I want to turn on the red. So if you want to turn on red, you put 100, means turn on the red. If you want to turn on the blue, the green, if you want to turn on the green, you put 010. If you want to turn on the blue, then you put 001. Okay, so how does this work? Let's look at the control RGB LEDs function. And let's look at the control RGB LEDs function. So the function is here. Function is here. Okay, this is the function. Let me copy this out, put it here so it's easier for you to see. So this is the function. 1, 2, 3, 1, 2, 3, 4, 5, 6, 3. Okay, so let's look at just one of them. Identical. So if R on is 1, if R on, that means R on is 1, right? Then you use the port B register. PCOR is this is it's like your FIO clear. Right? This is like your FIO CLR. Remember the LPC 1768? FIO CLR, you write a 1 there to clear the IO pin, right? And then the FIO set register, you write a 1 to set the IO pin, right? So this microcontroller, instead of FIO clear and FIO set, it's called PSOR, port set output register, and port clear output register. So how do you find this out? Okay, so you just copy PCOR, you go to the datasheet. Okay, I have this inside your datasheet folder. Go to datasheet, Control F, put in PCOR and port clear output register. Oh, that's the guy. So I just click him, and we got him. Port clear output register, PCOR. So what does this guy do? Okay, so it says here, there are 32 bits. Each one controls one IO port pin. Okay, if you write a 1, the corresponding bit is cleared to 0. Write a 1 to PCOR to clear that IO pin. PSOR, okay, let's see. PSOR should be the next one. PSOR, maybe it's up there. PSOR, oh, there you are. So PSOR, write a 1 to set to logic 1. Okay, so PSOR, write a 1 to set to logic 1. PCOR, write a 1 to set to logic 0. Okay, All right, so we come back here. Now we know. Now we know. Uh, um, I have this red. Red is at 18, right? Red is at 18. So red LED position, you know, is actually red LED position is actually 18, right? Is actually 18, huh? Okay. And mask 18 is actually 1 left shift by 18, right? So this is actually you are putting a 1 at pin 18. Sorry, not put a 1 at pin 18. You are putting a 0 at pin 18. And if you put a 0 at pin 18, you are putting a logic 0 at pin 18. Okay? You're putting a logic 0 at pin 18. So you put a logic 0 at pin 18, you are basically turning on the red LED. Okay? Now if you want to turn off the red LED, the LED is active low, ma. Active low, ma. You turn off means you put a logic 1. So put a logic 1 means you use PSOR. PSOR, write a 1 there, right? Write a 1 there. This actually like this. You're writing a 1 to bit 18 means you put a logic 1, means you put a logic 1 at pin 18. Okay, and off the LED. Right? So this would be you on the LED, and this would be you off the LED. Okay. All right. So now we know how to control the LEDs already. Yeah. How about, so the rest is the same lah. The rest is for green and blue is the same lah. All right. So how about the GPIO init? How about the GPIO init? Okay. How about the GPIO init? So the GPIO init function is this one here. Scroll to the side. Okay. This is the GPIO init function. The GPIO init function, you use a lot of registers to initialize the IO pins. So I explained the first one. The rest, you can find all the information from the datasheet. Let me just explain the first one. Okay, the first one is sim scgc5. So you notice the way the program is all the same one. So sim is probably a microcontroller peripheral. This microcontroller peripheral got some registers to control it. SCGC5 is probably one of those registers. So now I want to know, what's SCGC5? Why do I want to put this value in SCGC5? Okay, let me copy this out and we work this out. We work this one line out. The rest you can find everything from the datasheet. Okay, so first of all, I want to know, what is this? Sim SCGC5. What is this? What is this, guy? So I want to see what is this guy. We go to the header header file. Okay, this is mkl20. This is the mkl25z.h. This is the header file mkl25z.h. Okay, so what do I want to find? What do I want to find inside this file? I want to find what is sim scgc5 port b mask. I want to find this. So I go to this file, Control F, look for sim scgc5 port b mask. Oh, there it is. Got it. So let me copy this. Okay. So in mkl25z.h, sim scgc5 port b mask is actually this value. Okay. So what you're actually doing here is you are actually putting in this value. U means unsigned, unsigned. Okay. So this is actually equals to this value or with this. Okay. So what's this actually? A 100, 100, 100. This is actually 0B, 0100, 0000, right? 400 is actually this value. So what is this actually? This bit position what? This actually, this bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7, bit 8, bit 9, bit 10. So we want to set bit 10. No? We want to set bit 10. We want to set bit 10. We want to set bit 10 in SCGC5 register. Okay. So we want to set bit 10 in SCGC5 register. Now the question is why? Why? Why do we want to set bit 10 in SCGC5 register? So we find out what is SCGC5. Okay. So how do we find out what is SCGC5? We go to the data sheet. We go to the data sheet, right? Just go back to the first page. Search for SCGC5. So enter. Okay. System clock gating control register 5. System clock gating control register 5. So let's go to this guy. Okay. Aha, I found it. Bit 10 is port B. You can see this register. Bit 10 is port B, right? Bit 0, bit 1, bit 2. So bit 10 is port B. What is this port B? So we have to look at the description. We scroll down a bit to bit 10. Okay, what does it say here? Okay, so bit 10, port B. This is the port B clock gate control. This bit controls the clock signal going to the port B module. If 0 means clock disabled, 1 means clock enabled. So what we are doing now is we're actually enabling the clock signal to port B, right? You know these microcontrollers they are very power efficient one. So how to make it power efficient? The I/O ports can be turned off, right? Because if the I/O port is turned on, it's running, it's consuming power. So you can, by default, actually, all these ports are all disabled one. So if you want to use port B, which we want to use because we connect our LEDs to it, right? We want to use port B, you have to enable the clock signal to port B. So we have to put a 1 at bit 10 of this register to enable the clock signal to go to port B. Okay, right. So, oh, now I understand what this is for already. So this line is actually enable clock to B, right? So similarly, you can find out everything from the data sheet. I just show you one. We don't have enough time to go through everything. Okay, so this is your whole GPIO init. So there are a lot of steps here to initialize the port, but the first step is to enable the clock. The first step is to enable the clock to port B. Okay, so I see from the second step, this one is probably enable the clock to port B. Pretty obvious. So don't, okay, the rest are like that. Now let's look at the main program. Finally, we come to the main program. Main program. Okay. So what does the main program do? Now in your main program, so I bring you back to this. I bring you back to this. The main program is actually doing this. The main program is actually initializing the delays, initialize the GPIOs, check switch 1 press, check switch 2 press. Okay, this is your main program. Initialize delays, initialize GPIO, check switch 1, check switch 2. So let's go there. Okay, keep this in mind. Let's go there. Let's have a look. Okay. We initialize the delays. So we create two variables, W white delay and RGB delay. The default delay is slow, so we put in the slow value inside. And then we call the GPIO init function to initialize the IO pins. And then we check switch 1. Right? We check if switch 1 is pressed. If switch 1 is pressed, we turn on red, delay with the RGB delay. This is the RGB delay, which is the slow delay. Delay with the RGB delay. Call the delay function with the slow delay. Then you turn on the blue, delay again. Turn on the green, delay again. Now, if the button is pressed, if this is button not pressed, so you do RGB. If the button is pressed, Then instead of RGB, you're going to do red, green, and blue together, which is flashing white. Flashing white, the white delay, and then turn everything off, white delay. Okay. But if you press the second button, now this for second button. If you didn't press the second button, then the white delay and the RGB delay is the slow one. But if you press the second button, the white delay and the green RGB delay will be the fast one. Okay, so this is the program. Now, how would this program respond? What is the response of this program? Let's see. What is the response? This is the response. Okay, so the LED shows red, then it shows green, and then it shows blue, then it shows red, and then it shows green. Now, when it's showing green, you press the button. You press the button, but it does not immediately change to flashing white. There is a short delay before it changes to flashing white. Why? Because of the way you code. The way you code, the green has to finish first, the blue has to finish first before you go back. See, the green has to finish, the blue has to finish before you go back and check whether the button is pressed again, in which you realize that the button is pressed, so then you run white, not you the processor Okay, so there is a delay. How do we solve this problem? Okay, before we solve this problem, we need to restructure our program, because you see, the way we write our program is very bad. Okay, we are doing everything inside one big loop. Inside one loop, we are controlling we are checking for switch press, we are controlling the RGB, we are controlling the white, everything we do in one loop. Not good. So we should break our coding into separate parts, each one with a well-defined function. How do we break it? Okay, we break it like this. So we break it into three separate functions. One function just to read the switch. Another function is to flash white. Another function is to uh, do the RGB. Okay, each function got input and output one. So the read switches function, its input is switch 1 and switch 2. It will check switch 1 and switch 2. And then it will update the global variable. You see the G here, G is global variable. Global variable white, the global variable for flashing, and the global variable for RGB delay. So the white delay can be the slow delay or the fast one. RGB delay can be the slow delay or the fast one. Flash LED, this variable, the value is 1 or 0. If the value is 1, means you flash white. If this variable, the value is 0, means you do RGB. And both the flashing and the RGB, they control the LEDs. Okay, so if we break this program, how would we code it? Okay, let's look at the code. So the highlighted yellow part is how you break the program. Now you notice that here, just now we got three functions: Gpio, init, control, RGB, LED, and delay, right? Now we add another four more functions. One function is read switches, one function to flash white, one function to do RGB, and we also have another scheduler function. Okay, what's the scheduler function for? Now you see your main program. The main program now, you see, is so simple. It just call the GPL init, and then after that it call the scheduler. What does the scheduler do? The scheduler will, inside a loop, call read switches, flashing white, and RGB. So you call them like this. Now the function is the same, but it's more organized. Why is it more organized? See, so inside task read switches, you just check if switch 1 is pressed and switch 2 is pressed. Okay. Inside task flash, you just flash white, flashing white. Inside task RGB, you are just doing the RGB sequence. Okay. So as we guessed, there should be no change to the program. So the program response, you can see from here, is the same. Okay. But now you are running the task to read the switches, then you run the task to do flashing, then you run the task to do RGB. So because you didn't press the button, the button not pressed, so task RGB will run. So you do R, red, green, blue, and then you check, is button pressed? No. Do I need to flash? No. Do we need to do RGB? Yes. So red, green. Now, while it's showing green, no, you press the button. But as you know, lah, it won't respond until you check for switch press again. So there will be a delay, right? So how can we fix this delay? How can we detect the switch being pressed immediately? We can use interrupts, right? We can use interrupts. We detect the switch press using interrupt. So what happens? Okay, let's look at the code. We use interrupts. Okay, we use interrupts. So if we use interrupts, this is what happens. This is what happens. So the code to detect switch press is no longer a function. It is now an ISR. It's an ISR. So you didn't press the switch, the ISR, nothing happened. Okay. Do I need to flash white? No. RGB, yes. So you do red, green, and blue. Need to flash white? No. Need to do RGB? Yes. So you do red, and then you do green. Now, while you are showing green, the button is pressed. And you notice that when the button is pressed, the ISR runs immediately. But the thing is, the interrupt service routine just update the thing to do. It doesn't control the LED, right? The ISR just updates the variable to flashing white. You just update the variable to flashing white. It doesn't change the color. So when you return from the ISR, you resume back with the green and then the blue, right? And then you check whether need to flash white. You run the code checking whether to need to flash white, in which you need to, then only you change to flashing white. Okay. So why is our delay so long? The reason is because of the way we code. We have to go through the entire red, green, and blue. Can we reduce the delay? Yes, we can. We don't do all three red, green, blue. Whenever you call the task RGB, you just do one of the colors. Red, then you do green, then you do blue. Don't do them all at one go. What do we call this? We call this a state machine. We call this a state machine. So we have three states: red, green, and blue. So when you call the function, it will go red, do red first, and then you will finish. Then when you call the function again, it will do green, and then it will finish. Then you call the function again, it will do blue, then it will finish. So how does it look like in code? Okay, in code, it looks like this. Now, the RGB function, right? Instead of looking like this, this is your original RGB function. You do red, delay, green, delay, blue, delay. So you must go through everything. A better way is we break it out into states. So we check what is the current, what is the next state. So by default, the next state is red. So switch next state. If the next state is red, case state red, then you turn on red and you set the next state to green and you break, come out of this function. So this function only show red. When you call this function again, it will show green because that's the next state. When you call this function again, it will show blue. So what's the response? Our response should be much better now. As you can see from here, we are now checking the button press more frequently. It's more frequent, right? Because you see we break already. Now we check the button press. Need to do flashing white, need to do RGB. Okay, so you do red. Just do red only, we didn't do green and blue. Then we check the switch again, then flash, then RGB, do green, then we check the switch again, right? So now, when it's doing green, you press the switch, the delay will be much shorter. The delay is much shorter now, but there is still a delay. Why? Because you have to wait for the green to finish. Why? Because you are doing software delay. The processor is doing software delay. So when you're waiting for the green to finish, your processor is looping there, delaying, waiting for the delay to end. Processor cannot do other things. So it cannot detect the switch being pressed. Okay. How can we improve the delay? We can by not using the CPU to count delay. We use timers. Okay. So the timer that you use here the timer that you use here is the PIT, periodic interrupt timer. Okay. Now you can find out all about the PIT in the datasheet. The PIT is clocked by the peripheral bus clock. The PIT is clocked by the bus clock. So let's look for PIT. Let's look for, I just show you. I just go to the data sheet. We just look for PIT. PIT. Okay, so you can see from here, the periodic interrupt timer PIT, it is clocked by the bus clock frequency because this is the most important. This is the most important. When we want to use timers, or we have to know what is the timer's input frequency. This is the most important thing. We want to use timers to create delay, right? We need to know what is the timer's input frequency. So the periodic interrupt timer, his input frequency is the bus clock. Bus clock. So now I want to know what is the bus clock frequency. So I just copy bus clock. Okay, I go back to the first page. Put here bus clock. Bus clock. Okay, we search for bus clock. Bus clock. Bus clock. Bus clock. Bus clock. Bus clock. No, 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 no. Oh, there it is. Okay. So now I can see from here, you can see this this is your core clock, processor clock, processor clock. So the processor clock will be divided by a certain value before becoming the bus clock. So the bus clock is actually the processor clock divided by a certain value. CG is clock generator. CG is clock generator. So this is your processor clock is divided by a certain value. So how much is it divided by? I have to find out what is out diff 4. What is the division ratio, right? Out diff 4. So I go back to the first page again, put in out diff 4. Let's see, what is out diff 4? What is out diff 4? What is out diff? There it is. Okay, so out diff 4 is inside this register, system clock divider register. Sim CLK diff 1, whatever. So out diff 4, I want to know what is out diff 4. So let's look for out diff 4. Let's scroll down here. Okay, so this is out diff 4. What does it say? This field sets the divide value for the bus clock. All right, so it will divide your system clock. So if this out diff 4 is bit 16, 17, 18, so there is 8 different possible division options that you can choose. But what's the default one? So the default one is after reset, it is loaded with 0 if 1. 1 means divide by 2. So by default, your bus clock is your processor clock divided by 2 by default. If you didn't set anything, okay, by default. Divide by 2, system clock divide by 2. Okay, all right. So let's see. Now we code this by doing like this. We add another state. So you go to red state, and then you go to waiting red state. Then you go to green state, then you go to waiting green state, go to blue state, waiting blue, and then go back to red. So what is the waiting state? Let's see. See, the waiting state is this one. This is the waiting state. Okay, this is the waiting state. So every time you go to the waiting state, you will check if the timer has expired. This is a very bad way, but I cannot straight away make the program very complicated. I'm writing the program step by step. I make the changes bit by bit to show you. So here, we are checking whether the timer has expired or not. If the timer has not expired, then we come back and check again later, right? So your code become like this. Your code now become like this. Wow, our delay is super short now. You see, because we are checking whether the button is pressed. We are not using interrupts here. I keep things simple. So we check whether the button is pressed. You check whether you need to do flash or not. You check whether you need to do RGB or not. Then you keep checking. Right? You keep checking. So as long as the delay has not expired, because you keep going in to check whether the delay expired or not. So there's actually a lot more than this. This one is actually a lot. Okay, so when you press the button, right? Immediately after a very, very short delay, very, very short delay, immediately you will run because now you're running the task grid switches code very, very, very often. So immediately you will detect that switch on is pressed, and then you immediately change to flashing white very fast. Okay, very fast. But what's the problem with this code? The problem with this code is your CPU is very, very, very busy. Your CPU is very, very, very busy. It's doing a lot of things. So it's a waste of power. Now, how do we save power? Ideally, ideally, this is what we want. This is the ideal case. We want this. We want this. We want to only run code to do something useful. We don't want to run code that is not doing anything useful. So we only want to run the RGB code when you need to change to red. Run it again when you need to change to green. Run it again when you need to change to blue. Run again when you need to change to red. Run again when you need to change to green. And then when the switch is pressed, task grid switches will run to update the variable. After that, the flashing will run to change to white. Run again, change to black. Run again, change to white. Run again, change to not black, all off. So code only runs when it needs to run. This is the most efficient program structure. How do we achieve this? We achieve this by using an RTOS, which is next week's topic. So this is next week's topic. I just show you a bit. RTOS. And RTOS is a real-time operating system. It's where you think like this. This is you, right? You don't write a program like this anymore. You don't write a program where you do A, then you do B, then you do C, you go back, you do A, you do B, you do C. Don't write a program like this anymore. Cross. Remove this concept from your mind. This is the new concept. Okay? You write a program to flash RGB LED. You write a program to check switch 1 press. You write a program to check switch 2 press. Okay? And these three programs run in parallel. What? Is that possible? I only got one processor. How can I do three things in parallel? That's the secret of RTOS, right? The secret of real-time operating system is you don't actually do three things at the same time. You have the operating system program or the kernel is running in the background. Okay? You know your computer, when you press alternate control delete, you will see your operating system kernel. When you press alternate control delete, you will see your operating system kernel is running in the background. So you're actually running a lot of programs at the same time. You see now I'm running PDF, I'm running Internet Explorer, I'm running WhatsApp program, Notepad, I'm running lots of programs at the same time. But my computer only got 4 cores. How can it run so many programs at the same time? That's because you are doing pseudo multitasking. Pseudo multitasking means your processor run A program for 5 milliseconds, for example. Then it runs B for 5 milliseconds. Then it runs C for 5 milliseconds. Then it go back to run A again very fast. So it looks like all three programs are running at the same time, but they're actually running one after another, but they are being switched very fast. They are being switched very fast. Okay, imagine there are 10 of you eating on the table. 10 of you. You're all sitting on the table. You're eating. All of you have food in front of you. Okay, but I only have one fork and one spoon. So I give the fork and spoon to the first person. Then he start eating. Once his time is, each person can only have the fork and spoon for 1 second. I give him the fork and spoon for 1 second. So immediately he start eating. Then once his 1 second is up, I snatch the fork and spoon away from him. So he have to stop eating. You cannot eat already. Then I give the fork and spoon, of course, after I clean it, I give it to the second person. Now the second person get 1 second to very quickly eat. Then I grab the fork and spoon from the second person. I give it to the third person. So like this, the fork and spoon get passed from the first to the 10th person and then go back to the first person again. So everyone gets their turn, right? So it's like you have three programs running now. Each program get their turn of the CPU. They get a little bit of CPU time, we say. Okay, so it looks like they're running concurrently. So when we do RTOS next week, right, you have to move away from thinking about sequentially executing C code, right? Instead, we consider the things that each program needs to do. do and how data is shared between the programs, because we're going to write each one like an individual program. This makes your programming much easier if you're doing many things at the same time. Okay. All right. And that's the last part of your RTOS notes. Okay. So do you have any questions? Do you have any questions? Everyone okay? Testing, testing. Is anyone there? Okay, are you all okay? No problems. Do you understand this RTOS, this real-time system, how we write our program to deal with concurrency? We do multiple things at the same time. And then what happens as we introduce slight changes to the code? So we have covered all this already, right? So first of all, we wrote a program using the super loop, but it's a bad way of writing a program. So for better modularity, modular, we split the program to different task functions. Each function got a specific task, so we call it task-based programming. Then we add some other stuff to reduce CPU work and to have better responsiveness. Okay, right. How to let the program continue the color sequence after flashing white? This is the trick. That's a very good question. You see here, you notice that the code in this example, right? The code in this example, okay, this is not a good example. Let's look at this one. This is not a good one also. Let's look at this one. Is this a good one? No. Uh, red, green. Okay. Never mind. I just you go back to the first one. Okay. Red, red, green, blue, red, green. No, this is not good. I use this one. Okay, so actually your question is, you see, here is red, and then green, and then blue, and then red, and then green. You see green here, we are interrupted halfway, right? So we got a little bit more green to go. We are interrupted halfway. So you change to flashing white, right? So after you finish flashing white, if you release the button, you should continue and finish off the last bit of green, and then you should change to blue. But the program here, he didn't continue back with the interrupted green. He straight away restart again with red. So this is not what we want. In your assignment, you need to continue back with the previously interrupted color and duration. So this guy, if he got a little bit more left, you need to do the resume and finish that little bit left. How do you do that? That's the challenge. I cannot give you the answer. So you got the concept correct. Yes, that's the thing that we want to do. We want to continue the color sequence. So how do you continue the color sequence? You need some variables. You need some variables to keep track, to store the program state before the interrupt. Then after the interrupt, you have to resume the interrupted program state, right? So you need to store something before the interrupt. So why is it you need to store? That one is up to you because it's an open-ended assignment. You can do it in any way that you like. Okay. In fact, you don't even need to store a global variable for the to save the program state. You can use some other approach also. Okay. Right. Good question. Thanks. Any other questions? Now we ran out of time to discuss the quiz 7. No worries. We will just look at the quiz 7 on our next class. Or do you have a class now? If you don't have a class now, we can spend 5 to 10 minutes to go through quiz 7. Okay, no class. Is everyone okay if we spend another 5 minutes to discuss quiz 7? Okay, all right. Let's quickly go to quiz 7. Quiz 7, quiz 7. Let's quickly go there. Quiz 7. Yes. Oh, two haven't turned in yet. Now, I know that actually you submitted already. Press the submit button. Okay, class. I need this to take your attendance. Okay, I know you have finished the quiz already, but actually sometimes some of you forgot to press the submit button after you finish the quiz. You need to press the submit button to get the turn in result. Okay, so those of you go and check now. See you got press the submit button or not. If you didn't press the submit button, press it. Okay? Press the submit button, right? Okay, so let's go to the quiz. Remember, those of you who haven't pressed the submit button, press it. Now, let's look at the first one. Uh, what is the purpose of using port PCR mux mask in GPIO initialization? Why do you want to use port PCR mux mask? Okay, let me copy this out, port PCR mux mask, and we look inside here, header file. We go to the header file, we search for port PCR mux mask. Let's go to the top, click here, search for port PCR mux mask. Okay, there it is. So port PCR mux mask, port PCR mux mask is 700, which is actually in binary 0111 0000 Okay, so what is this for? What is this for? Let's look at our notes. Let's look at our notes. What is port PCR mux mask for over here? Okay, this is the code. I copy this out and I paste it here. Let me paste it here. Okay, so this is actually to make the pins GPIO. You got 5 pins. The LED got 3 pins. LED got 3 pins. Push button got 2 pins. Push button got 2 pins, right? So you need 5 GPIO pins. Okay, so let's look at the first one. This is port B PCR 18. Port B PCR 18. So each pin got a PCR register. We have to look at what is the PCR. Let's go and look at the PCR now. We look at the PCR. What is the PCR? What is the PCR? What's the PCR? Okay, PCR. So pin control register, PCR. Each pin got its own pin control register. So X is the port. X can be port A, port B, port C, port D, right? N is the pin number. So you got port A, pin control register 0 for pin 0, port A, pin control register 1, port A, pin control register 2, all the way until port A, pin control register 31. So each port can have up to 32 pin control registers. Okay, so now let's look at this pin control register. Pin control register. You see, we got 111 here. What's that? This 111. This is bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This 111 is at bit 8, 9, 10, right? It's at bit 8, 9, 10. So you see here, this value, this port PCR mux mask is actually this value. Is actually this value. Is actually this value. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay. It's actually this value. All right. Is this value? This is your port PCR mux mask, right? This is your port PCR mux mask. This is the value. This is the value. Okay. Now you notice we invert it. We invert it. So if you invert it, what happens? It becomes 1111, 1111, 1111, 1111, 1111. Invert 1000. Okay. 1111 and 1111. So we put this into port B PCR 18. We are clearing the mux field. Correct or not? You end, you end. So you see, this one is equals to this one and with this value. Right? This is the AND operation. You are taking this one equals to this one and with this value. So what you are doing, you are clearing these 3 bits. Why are we clearing these 3 bits? We need to clear these bits and then we put the value inside. Why we need to clear it first and then put a value in? What is this mux for? What is this mux 8, 9, 10 for? What is it for? Okay, this one is for. Let's scroll down. Okay, there it is. So this mux 8, 9, 10 it's for your pin select. It's just like your STM32F, the pin select register, pin selection. So you got 8 alternative functions. If 000 means analog function, 001 means GPIO function. These are the other specific functions. You have to check the data sheet, other sections. So we want GPIO function, we put a 1 there, put a 1 there. That's why you put a 1 inside here. But before you put a 1 inside there, you have to clear it first. So that's what the port PCR mux mask is used for. It's used to clear the mux field. Used to clear the mux field. Okay? So it's used to clear the mux field. Okay, to clear the mux field. Okay, that's what you use it for. Clear the mux field. Okay, next one. Which of the following features of MCU peripherals provide the least support in reducing CPU utilization? Now, peripherals, they help your processor do things. So your processor don't have to do it itself. So you can reduce the processor utilization. You don't have to use the processor for everything. How? If you want to synchronize task execution, you can let a timer do this. If you want to detect asynchronous events, you can use interrupts. You want to generate time-triggered signal generation. You want to generate signals periodically. You can use timers for this, right? But what you cannot do is accelerate peripheral setup, right? You do not have microcontroller peripherals that accelerate the configuration of other peripherals. I repeat, there is no such thing as microcontroller peripherals that accelerate the setup configuration of other peripherals. There is no such thing as peripherals that accelerate the configuration of other peripherals. No such thing. It's wrong. Okay? It's wrong. Right. Why there's no such thing? People can make it right, but why people don't make it? That's because you only set up microcontroller peripherals one time. When you turn on the microcontroller, you only set up one time. You never do it again. Why do we want to create peripherals to do something that we only do one time at the beginning? Total waste of resources, right? So that's why we don't need it. Okay. Right, next one. Which of the following characteristics of super loops interferes the least? So super loops are very bad. They are very bad because no priority. Everything that you put inside the super loop have the same priority. So high priority tasks do not get the attention that they need. And super loop, the tasks also interfere with each other. If you put task A, task B, task C inside the super loop, task A will interfere with B and C. If task A is running, B and C cannot run. If B is running, A and C cannot run, so they interfere with each other. And then the loop execution time is also not constant. Because task A, task B, task C, they may have some conditions. So sometimes the condition is true, sometimes the condition is false. That's why every time you run the loop, the execution time might be different based on the condition. Right? So you cannot use your loop, you cannot assume that the loop has a constant execution time and then use that for your timing delay, because the loop will run differently every time. Okay? So all these are how superloop interferes with real-time operation. Okay? Which one does not interfere is low priority tasks. We put them inside the loop. Normally, a low priority task will put in the loop. High priority task, right? We assign to interrupts. Okay? Right. Now, the next one. If I'm using a real-time operating system to run the different tasks, task read switches, task to flashing white, and task for RGB. Now, in an RTOS, you can assign priority to task. Right? The important task can always run first one. So who is the most important? from the lowest to the highest importance. Now, the task that takes the longest to run, normally we put it as lowest priority. The task that is the fastest and always need to run, if the signal comes, you put that as highest priority. So logically, RGB, which is the slowest, we will give it lowest priority. The switches, task to read the switches, we will give it highest priority. And flashing white, which is faster than RGB, we put it medium priority. Okay? That means if your processor is running task RGB now, if task flash and task read switches need to run now, the processor will run task read switches first and then run task flash. Okay? If you set the three of them as the same priority, then if task read switches need to run, but the processor is currently running task RGB now, it will have to finish RGB first before it run task read switches. If you set them same priority, right? So no good. So we should give this guy highest priority, this one lowest, this one medium priority. That would be logical. Okay. All right. Next one. How does the finite state machine technique? Well, actually, finite state machine sounds like very classy like that, but it actually means it's the program. You don't run it all at one go. You split it into different states, right? So that's why you call it a state, lah. And then why you call it a machine? Because it is just doing things mechanically, right? It's either in this state or that state based on conditions. So it's a machine, right? It follows rules. So it's a state machine. And then finite because you have finite states. We only got three states, red, green, and blue. If you add in the delay, we got six states. Red, red wait, green, green wait, and blue, blue wait. We got six states. So that's why it's called a finite state machine. Okay. Uh, to explain what it is. So how does the FSM help to improve responsiveness? Because we only execute one state whenever the RGB task run. We don't do red, green, blue. We do red, then we exit. When we come back, we do green, then we exit. When we come back, we do blue, then we exit. So this will make you check the switches more often. So you can respond faster if you check the switches more often. Okay, so FSM help to improve overall responsiveness because we only execute one state whenever the RGB task runs instead of all three states. Okay, right. Next one. How does the PIT module, how should the PIT, the periodic interrupt timer, be configured so you time out every 1 second? Okay, I want to time out every 1 second. Call frequency is 48 megahertz with default setting. Okay, for call frequency is 48 megahertz. So default setting means uh, the bus clock is half of call frequency. So if call frequency is 48 megahertz, that means my bus clock is 24 megahertz. So my timer is running at bus clock. So my timer is running at 24 megahertz. So if I want it to time out every 1 second, the reload value should be 24 million. Okay, the timer is running at 24 megahertz. That means the timer is receiving 24 million clock pulses per second. That means it's counting 24 million times per second. So if you reload it with 24 million, it will time out every 1 second. Okay, logical. All right. Okay, use some time to absorb. Need some time to absorb that. Okay, all right. I think this is the last one, or not the last one. Which of the following methods we do not use to improve responsiveness? Polling to detect external event. Okay, if you use polling, that means you check whether something has happened or not. You will not detect the thing happening until you run the code to check. That's a bad idea. So polling is not good for responsiveness. Right? You only detect that something happened when you run the code to check it. If you don't run the code to check it, you won't know it has happened. So that's polling. Okay. Lastly, this is the last question. What is the interrupt number of port D IRQN? Copy this. Port D IRQN. Copy this. paste into header file, the answers in the header file. Okay, paste this into the header file. Look for port DIRQN. Okay, found it. So port DIRQN is interrupt number 31. Okay, so these are all your interrupt numbers. And again, we don't use numbers because if you write numbers in your program, nobody understand what those numbers are. So instead of using numbers, right, C programming has a special concept called enumeration. Enumeration means you can create a list where you represent an integer with a very nice, meaningful name. Okay, enumeration. You can create a list of enumerate one by one. You can list one by one. You can replace a specific number with a nice, meaningful name. So instead of the number 31, we call it port dirqn. So whenever you use port dirqn, the compiler knows that this is actually the number 31. Okay. All right. So it's 31. Yes. Okay. That's great. Right, class. Okay with the quiz. Any questions before we stop here? Oh, okay. All right. No questions. No worries. If you thought of any question later, just WhatsApp or email me lah. Okay. So I will stop here for today and see you in the next class. Okay. Thanks everyone for coming. Okay. Bye everyone. Oh, before that, did I miss anyone's attendance? Go Kian Sing, are you here? Go Kian Sing, are you here? Go Kian. Yes. Okay. Wait. Lim Chun Wei. Lim Chun Wei, are you here? Lim Chun Wei. Lim Wen Yang. Lim Chun Wei and Lim Wen Yang, are you here? Lim Chun Wei, Lim Wen Yang, Lim Chun Wei and Lim Wen Yang. Wen Yang. Oh, Wen Yang is here. Chun Wei, are you here? Chun Wei is not here. Uh, Maybe he logged out. Anyone can help me check with Chun Wei? You got his WhatsApp number. Can you check with Chun Wei whether he was here just now and then he left? Class rep, class rep or course rep? Anyone? Can you just send him a quick WhatsApp? Maybe he logged out already. Just now I forgot to call his attendance. Okay. Right, can help me check now? Oh, he's taking leave. Oh, okay. What is the reason? What is the reason? Oh, okay. Never mind. I just indicate as a. I just put in as a leave. I think he sent me an email to check. I'll call him. Okay. Thanks everyone. Thanks everyone. Okay. Never mind. I'll check with him. Thanks everyone.